Module 1, Lecture 3. So today we will be starting up with summing amplifier. So what is summing amplifier? An amplifier whose output is the sum of the inputs is called as summing amplifier. Now by having a look at the circuit, you can observe that there's an ideal op amp with a feedback resistor connected between the inverting terminal and the output terminal. And at the inverting input terminal, we have three resistors connected to it, that is R1, R2 and R3, with the applied voltages V1, V2 and V3 respectively, along with the currents flowing through them I1, I2 and I3. And there's also current IB flowing through the op amp. The current flowing through the op amp will be 0, as we already know that the impedance of the op amp is 0 and your open loop gain is infinity. So your current flowing through the op amp will be 0. Now coming to the derivation part, by applying KCL at node A. So when you apply KCL at node A, you get the step number 1. That is II is equal to II, in the sense we are taking the complete currents, whatever it's flowing, no, all those currents being taken. II is equal to IB plus IF. In your step number 2, we will be substituting IB is equal to 0. As we already know, the current flowing through the op amp is 0. So you get II is equal to IF. Now II will be equal to I1 plus I2 plus I3. This is your currents flowing through the resistors R1, R2 and R3. Now substituting your II, you get the step number 3. So I1 plus I2 plus I3 will be equal to your IF. Now step number 4, your I1 can be written as the voltage entering through that point, that is V1 minus, it ends at the point VA. So V1 minus VA by R1 plus, in the same way, V2 minus VA by R2 plus V3 minus VA by R3, which is equal to VA minus V0 by RF. Now we know that your VA is equal to 0. That is based on the virtual concept, because your terminal B, that is non-inverting terminal, is been grounded. So at that terminal your voltage is 0. Based on that concept, your voltage at the terminal A will also be equal to 0. So you get step number 5, that is V1 minus 0 by R1 plus V2 minus 0 by R2 plus V3 minus 0 by R3, which is equal to 0 minus V0 by RF. Now step number 6, we get V1 by R1 plus V2 by R2 plus V3 by R3, which is equal to minus V0 by RF. Step number 7. Here we only need the output voltage. So segregating other components to the other side, we get V0 is equal to minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. Here you can note down one point. If all the resistors are equal, that is RF is equal to R1 is equal to R2 is equal to R3, then your total output voltage will be equal to V0 is equal to minus of V1 plus V2 plus V3. That is nothing but, in simple way, we can say your total output voltage will be equal to negative sum of the voltages. Now coming to the difference amplifier. An amplifier whose output voltage is proportional to the difference of the input voltages is called difference amplifier. Now this difference amplifier is also called as subtractor. Now by having a look at the circuit, you can observe there is an ideal op amp with feedback resistor RF connected between the inverting terminal and the output voltage terminal. Now At the inverting terminal, we have a resistor connected to it, that is R1, to an applied voltage V1 and along with the current I1 flowing through it. Now, at the non-inverting terminal, we have two resistors connected at that point, along with the applied voltage V2 and the current flowing through that is I2. Now, these resistors R2 and R3 are in series with each other. Now, coming to the derivation part, it won't be same as the previous one because in previous circuits, one of the terminal was grounded whereas the other one was given to the input voltage. In this case, both the terminals are applied to the input voltages. So, observe carefully. Case 1. Considering V1 alone and V2 grounded. The difference amplifier acts as inverting amplifier. Here in short, I have written AMPR for amplifier. You can consider it as amplifier. So, the case 1, what is it saying in the sense? We should assume that the input voltage is applied only to the inverting terminal of the op amp, whereas the non-inverting terminal of the op amp is grounded. By assuming in that way, your complete circuit will act as an inverting amplifier. Therefore, your output voltage will be V01 is equal to minus Rf by R1 into V1. That is your output of an inverting amplifier. Case 2. Considering V2 alone and V1 grounded, the difference amplifier acts as non-inverting amplifier. Now, what is it saying in the sense? Now, we should assume that the input voltage is applied to the non-inverting terminal of the op amp, whereas your inverting terminal is grounded, so that your complete circuit will act as a non-inverting terminal. Therefore, your output voltage will be V02 is equal to 1 plus Rf by R1 into VB. VB, why did we take in the sense? At that terminal B, we have a voltage VB. So, we'll be considering VB. So, this VB is nothing but V2. Now, to achieve your VB, step number 1. VB is the voltage drop across R3. Therefore, basically we will be applying the voltage divider rule across those resistors because the resistors R2 and R3 are in series. So by applying voltage divider rule, we get VB is equal to total voltage, that is V2, into across which resistor are we finding, that is R3, by sum of the resistance, that is R2 plus R3. Now step number 2. So in this step, we will be substituting the VB value. Therefore, your V02 will be equal to 1 plus Rf by R1 into V2 by R2 plus R3 into R3. Step number 3. By superposition theorem, your V0 will be equal to V01 plus V02. So as far what the cases which we applied comes under superposition theorem, because we considered one as active and the other as grounded. That is your superposition statement. Therefore, your V0 will be equal to, substituting your V01 and V02 values, we get V0 is equal to minus Rf by R1 into V1 plus 1 plus Rf by R1 into R3 by R2 plus R3 into V2. So this is the final output voltage of an difference amplifier. Now coming to the instrumentation amplifier. An instrumentation amplifier is used to amplify very low level signals by rejecting noise and interference signals. Now have a look at the circuit. Observe carefully, it has two stages, stage 1 and stage 2. At the stage 1, there are two ideal op amps with the non-inverting terminal applied to the input voltages. If you observe, the first op amp is been applied to an input voltage VA and the second one to an input voltage of VB, and it has a resistance of R1, R2. So your R1 is your feedback resistor and R2 is your input resistor. And whereas your R3, it is your feedback resistor for the second ideal op amp. And these outputs are connected to your second stage of the ideal op amp. In the second stage, you have a difference amplifier. So this difference amplifier consisting of resistance R4 at the inverting input terminal, R6 and R7 at the non-inverting input terminal, R5 as your feedback resistor, and we have a load resistor RL at the output. Now to achieve total voltage gain, we have a derivation in steps. So here it's step 1, voltage across resistor R2. In the stage 1, your resistor R2 will act as an input resistor. So at that input resistor, your voltage is nothing but the input voltage. The input voltage will be flowing. So VI is equal to VA minus VB. So why we are considering both of them? Because there are two ideal op amps. The first op amp is of with VA applied voltage, and the second op amp is of with VB applied voltage. So your input voltage will be VI is equal to VA minus VB. Step number 2, current through the resistor R2. I2 is equal to input voltage to the R2. Step number 3, differential output voltage. So differential output voltage, in the sense we will be applying superposition theorem to the resistors R1, R2 and R3. So your voltage will be V0 is equal to VR1, that is voltage across R1, plus voltage across R2 plus voltage across R3. So your voltage across R1 is I2 into R2 because the same current is flowing, plus I2 into R2 plus I2 into R3. Now by taking I2 common out, we get V0 is equal to I2 into R1 plus R2 plus R3. Step number 4, substitution of I2 in the above equation. So you get V0 is equal to Vi by R2 into R1 plus R2 plus R3. Now by considering R1 is equal to R3, therefore it implies your output voltage will be equal to Vi by R2 into R1 plus R2 plus R1. Now voltage, total output voltage will be at the stage 1. This will be your stage 1 output voltage. So V0 is equal to Vi by R2 into 2 times of R1 plus R2. And your gain from the output voltage will be V0 by Vi is equal to 2 times of R1 plus R2 by R2. Step number 5, voltage of difference amplifier. So this will be at the stage 2. At stage 2, we have a difference amplifier. So your output voltage will be V0 is equal to R5 by R4 into V2 minus V1. That implies it is your gain also. Now step number 6, total voltage gain. So your total voltage gain, we have a formula. A is equal to A1 into A2. Now by substituting your stage 1 and stage 2 gains, you get the total voltage gain as A equals to 2 times of R1 plus R2 by R2 into R5 by R4 into V2 minus V1. We can note down few applications of instrumentation amplifier. Number 1, instrumentation amplifiers are used in data acquisition from small output transducers like thermocouple strain gauges, measurements of Wheatstone bridge, etc. Second point, these amplifiers are used in navigation, medical, radar, etc. These amplifiers are used for imaging as well as video data acquisition in the conditioning of high-speed signals. They are also used to enhance the signal to noise ratios in audio applications like audio signals with low amplitude. And these amplifiers are used in RF cable system for amplification of high frequency signals. And some examples of this are they are used to measure heartbeats, blood pressure, temperature, earthquakes, and so on.